it's very nice to meet you. Sorry I can't be there in person, but thank you for attending this event. I'm very excited to tell you a little bit about my experience in working on foundational technology that is starting to become have a potential impact on our lives. A new field called quantum computing and the future of technology that might change. My name is Jung-Sang Kim. I'm a co-founder and serving as a Chief Technology Officer at IonQ, and I'm also a professor at Duke University. Quantum computers promise the ability to solve problems that were thought to be impossible, and I'd like to salute to you what type of changes in our lives that could be brought about using this very interesting and somewhat unique technology. So we know all of us use computers. Actually, the fact that this event is possible during the pandemic is all thanks to digital technology and communication technologies. And classical computing has been the backbone of modern society. We use all of these devices today on a day-to-day operation. It gave us the personal computer, the internet, digital e-commerce. It put robots on Mars and smartphones in our pockets. It drove the economy and financial markets during the information age. Regardless of how powerful classical computers are, there are very important problems that classical computers will never be able to solve. And here I say never, because these problems are so vast in scale, the capabilities of our computational power is as powerful as it is today, we will not be able to tackle these problems. Some of the world's greatest problems and challenges, and therefore opportunities, would require building classical computers larger than the universe itself. The possibilities that we have to explore are so vast that it just is impossible to fathom computational capabilities. And therefore, a new paradigm of computing is needed. So quantum computing has the potential to solve many of these currently intractable problems, from logistics to materials to machine learning, to the market for full-scale fault-tolerant quantum computing. Again, this is a lot of words. If we can make quantum computers that have its full-blown potential power, the potential to make an impact will be immense. It is currently looked at it very much from the scientific application point of view, but there are many more commercially viable applications in quantum chemistry, simulations, algorithms, and quantum machine learning, where this could have a huge impact. So this original idea of quantum computers came from Professor Richard Feynman. He is a very famous physicist, was at Caltech. He was awarded the Nobel Prize. He says he realized that some of the computational problems we have to study nature is just very, very difficult. And he said, nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical, because quantum mechanical computers are much more powerful. It is a wonderful problem because it doesn't look easy. It is a very difficult problem to build this type of a computer. So let me give you an example of how powerful potentially a quantum computer is. So here I give you an example of what's called an unsolvable problem, which is known as factoring. A factoring is a problem where if I give you two numbers, we can multiply two numbers and get its product. And that is a relatively easy problem. We actually learn how to do that in our elementary school. And the same algorithm applies no matter how big the problem is. But if I give you a product of two numbers and ask you to find the two factors of that number, it turns out that that problem is very difficult. Although multiplication and factoring are the opposite direction of the same problem, it is very easy to go one way, but it is almost impossible to go the other way. And this is sometimes this is called a one-way function. It's very easy to go one way, but very difficult to go the other way. And this type of one-way functions turn out to be very helpful for building cryptosystems. And by cryptosystems, I mean the encryption that we use to exchange information in the open internet, still keeping that information safe. So for example, if I go on to online shopping and buy something and send my credit card information over, that credit card information gets encrypted. And although the encrypted message can be visible by anybody in the internet, it is very difficult to decipher and gain the message that was being sent. And of course, there are more than $2 trillion worth of financial transactions that are happening every day in this world using this encryption. So it is a very practically important technology. It turns out that the factoring problem is really hard. For example, a practical encryption actually is based on the fact that factoring very large numbers is difficult. The way that it is difficult is if you take a typical encryption that is used today, it takes computers billions of years, almost approaching the age of the universe, to actually crack this code using the computational technology today. And when it's that difficult, you say, okay, that is impossible. Okay. And it doesn't get any easier even if we have Moore's law, meaning classical computers get exponentially more powerful. Still, by going to slightly bigger problem, the problem scales so challengingly fast that it is impossible to crack this code. However, and that's why we say classical computers will never be able to solve this type of a problem. And therefore, we very comfortably think that the encryption system that are used in e-commerce today is very safe. However, this problem is very difficult for classical computers. However, if you are able to make a quantum computer that can actually big enough and powerful enough to solve this problem, the principles of quantum computer allows you to solve this in an instant. And therefore, there is an example of a realistic problem that quantum computers can solve that classical computers can never do. And it turns out there are many other such challenging problems that have everyday impact that I'll give you some example of. And therefore, creating this quantum computer can potentially unlock a massive opportunity for improving our lives. So I'd like to start giving you a brief preview of what a quantum computer may look like. Now, if you think about today's most powerful computers, then you think about either data centers or supercomputers. And this is a picture of Google's data center. And you can see that there are thousands and thousands of computers that are connected together, which gives you a very powerful computational capability. Now, so this is what we think about computers today. But if you roll back the clock just about 60 years ago, and think about computers in 1960s, you actually see a picture like this in the 1950s and 60s. And NASA, when you think about computers, these are people who compute. These are, back then, we did not have computers of this type. And the computation for trajectory of rockets and spacecraft were indeed computed by people by using paper and pencil, okay? So these were very talented women, mostly, who were doing these computations. But we think of computers very differently back then than it is today. Now, it turns out that the next generation of computers may look just as different as these modern day computers are from computers from about 50 or 60 years ago. The next generation computers, based on quantum principles, may look something completely different. So there's no reason to believe that the next generation computers will look anything like a traditional computer that we use today. It turns out that even if the people who used to compute and the machines who compute numbers, even if they look very different, they still rely on the same principles to do the computation. And this is basically representing numbers and information by bits, and then computing whether the bit is 0 or 1. Turns out that when you go to quantum computers, you use a fundamentally different principle to do computation. And this actually gives you some superpowers that classical computer does not have. So let me give you a sense of what those superpowers that the quantum computing brings to the table in a very illustrative way. All right. So first of all, a bit is a representation of information. So it is either a 0 or 1, and it is a basic ability to distinguish two different states. A quantum bit is something much more complex than that. It still has two basic states, 0 and 1, but it actually can exist in what's called a superposition of the two states at the same time. It can store both 0 and 1 at the same time. And this ability to store different states at the same time gives you an exponentially large storage capacity compared to the classical bit. And it also allows massively parallel computing, much larger than classical computers can ever provide. And that allows you that provides the possibility for us to solve and tackle hard problems, such as optimization. So where does the quantum computing superpower come from? There are two kinds of superpowers. One is the superposition principle. And this means that if you have a quantum bit, instead of the bit being at 0 or 1, it can actually be in a arbitrary, what's called the superposition of 0 and 1. So you can multiply the first state by a number a, and the second state by a number b, and then you can add them up. Of course, if a is 1 and b is 0, then you actually recover a 0 state. If a is 0 and b is 1, then you recover the 1 state. However, if a and b are not 0 or 1, then you can actually represent both states at the same time. Okay, so how do you think about it? It actually is, there is a little bit of a mind game that can tell you what this quantum computing may look like, this quantum bit might look like. So you think about this cube where I'm only showing the edges, and it can actually, your mind can interpret this cube in two different ways. For example, you can interpret the cube this way, where the front facet is sticking up, or you can actually interpret it this way, where the front facet is pointing upwards. Now, before you go, it is unclear which one of these two possibilities are this cube is taking. And quantum bit is just like that. It actually it can contain both of those possibilities together and carry out the computation as if you can actually represent those two possible states at the same time. And that's called the superposition principle. And this actually is one of the superpowers of quantum computer. I call it superpower because just like in Avengers movies, we think about these superheroes having very unusual power, which none of our human beings have. But if you imagine and accept what those powers are, then you can imagine what they can do. For example, a Superman can fly. And you can think about a lot of interesting things you can do if you accept the fact that there is a person who can fly. Okay, so quantum computer is just like that. It is not clear. We do not experience this kind of a superposition on a day-to-day basis. But if you go to the subatomic world, this superposition is the very nature of how the subatomic particles behave. So if you accept the fact that this type of superposition is possible, then you can imagine using them to do a very interesting computation. Now, the second superpower is called the entanglement. And the entanglement means if you actually have two quantum bits, in this case represented by the internal state of an atom, for example, you can now have a principle where the state of this can be very strongly correlated. If you think about this state, it can actually be in 0, 0 or 1, 1 at the same time. This means that if one of the atoms is 0 in the 0 state, then the other qubit is also in 0 state. If the one of the qubit is in 1 state, then the other one is also in 1 state. And therefore, the two states of the two qubits are always exactly the same, although you do not know whether it's a 0, 0 state or 1, 1 state. And this type of a very strong correlation between multiple particles it does not exist in classical world. However, in quantum world, this type of very strange behavior actually persists. So you can actually represent this as being 2 squared at this time, because now we have 2 qubits. And this quantum state that is entangled says that either both of these are in this one of these square states, or both of them in those other square states. But it does not exist in a way where one of them is pointing front and the other one is pointing up. Now, this is all very confusing. It doesn't look like whether this is real, but if you're confused, you're not alone. Even Albert Einstein, the great physicist of the last century, thought this was a spooky action at a distance, meaning that there will be correlations that are fundamental, that are separated by and can be communicated by faster than speed of light. So he could not come to grips with the fact that entanglement is real, right? So this is a very strange behavior, but ever since Einstein, the physicists have created many different experiments to show that this type of entanglement indeed exists in the quantum mechanical world. So basically, by utilizing these two superpowers, we can actually start to do computations that are not possible in the classical world. So how powerful are these superpowers? So now let's think about the quantum state of 20 qubits. Okay, it turns out if you have 20 of these atoms, 20 qubits, in order to represent and describe the state of 20 qubits, you need about 8 megabytes of memory space in a classical computer. And today, of course, we have many, many more than 8 megabytes of computational space on a small cell phone that we carry in our pockets. So that's very easy. Now, by the time we get to 50 quantum bits, the possible states that 50 quantum bits using this superpower can describe corresponds to about 9 petabytes of memory, and petabyte is very large number. It's basically a million billion bytes of memory, and you really need some of the largest computers that we have today to describe this state. Only merely 50 quantum bits. Now let's think about a few more qubits. Now, if the quantum technology can evolve, and let's say we can put together a quantum computer with 160 qubits. Now that requires the memory of about 10 to the 50 bytes of memory. And this is basically 1 followed by 50 zeros. And it turns out that this is a very large number. It actually corresponds to the number of atoms on Earth. So if you want to think about a classical computer that is presiding or that can describe the quantum state of 160 quantum bits, we literally have to take every atom that we have on Earth, convert them into 1 bit of classical memory, and you can barely make that description. Of course, at this point, you can say that no matter how large of a classical computer you can ever build, you cannot match the possibility of a quantum computer with just 160 quantum bits. Okay, this is the kind of massive parallelism and computational power a quantum computer will provide. So these are very powerful things. So if you look at the economic engine of our computational power that was driving a lot of our economy over the course of the last 30 or 40 years, we call it the Moore's Law. This is where computer chips get faster and more powerful by about a factor of 2 every 18 months. That's called Moore's Law, and that has held through the 80s and 90s and 2000s. But we can clearly see that over the course of the last 15 years or so, the rate at which computers get more powerful has certainly been slowing down, right? So even with Moore's Law, there are very important problems that will always be beyond the reach of standard computers. And these are important problems like optimization of logistics, material functions, and studying chemical structures. A classic example is this traveling salesman problem, where if you are given the task of going through a certain number of states or cities that you have to travel, what is the most efficient way or shortest path to pass through all of those cities? It turns out that the number of possibility grows very, very quickly as you add the number of cities that you have to visit. There's also very novel material design challenges. For example, if you're trying to come up with the next generation material systems or trying to understand the chemical reaction or that is useful for making pharmaceutical chemicals and things like that, those turn out to be extremely challenging computational problems because the underlying mechanism is all quantum mechanical. But it turns out that these material and chemistry problems are prevalent in our everyday lives today, and there are huge industries that are struggling with these types of problems. So so in the last maybe 20 years or so, people have come up with various ways to create quantum computers, and these are computers that can compute using these fundamentally quantum mechanical principles. IonQ's technology is shown here. You can see that this is a little chip, a computer chip. This is actually a silicon chip that is designed to hold individual quantum bits. Our quantum bits are individual atoms. You can see that this actually represents about 80 individual atoms that are floating in free space, right? The separation of these atoms is about 5 micrometers, which is about 1/20th the width of your hair. And therefore, 80 quantum bits here will occupy about 0.5 millimeter of space. So all of these quantum bits, because they're individual atoms, they can be crammed into a very, very tight space. Now, the fact that you can jam these kind of qubits in the same place does not necessarily mean that you have a quantum computer. We need an ability to control these quantum bits. And these in our quantum computers, they are these individual atoms are used as quantum bits, and we have a fully flexible control of these things by using electromagnetic fields, mostly laser beams. So this shows our ability to control these qubits. This photograph underneath shows our quantum computer chip that you can trap these individual atoms. We're loading individual atoms from on this area, and then we're bringing them up to this quantum zone. And in this example, we've shown that we have basically loaded 23 individual atoms, and then we make them into a very straight and uniform linear array. And this becomes your computational substrate on which you can do the computation. So we have the ability to manipulate individual atoms at this scale using the cutting edge microfabrication technologies. Now, how do you control this thing? This shows a little video of how we control these atoms. We start from a single laser beam that we split into multiple ways, in this case about 32 beams. And these individual beams are tightly focused onto this chain of atoms. And then as you start the computation, we initialize all of these atomic qubits into the identical state. And as you do computation, as you do quantum logic gates, just like in the AND gates and NAND gates in digital computers, we actually shine laser beams to the appropriate atoms, and that will actually manipulate the internal states so that you can carry out the computation. And this is fully performed by digital programming of these laser beams and tailoring the laser beams to enact these operations. And then at the end of the computation, you shine a specific laser beams, and some atoms will glow and the other atoms will stay dark. And when the atoms glow, you know the quantum mechanical result of the computation is 1. When they don't glow, the result is 0. So we can actually read out the information from individual atoms at the end of the computation. And this is how the flow of the quantum computer will go. So I'd like to think about, what are some of the interesting problems we can solve in using quantum computers. I gave you examples of factoring. I gave you examples of materials and chemistry simulations. But there is also a very interesting direction of this machine learning that we can think about. Now, if you think about machine learning today, it is enabled by our ability to access a massive amounts of data that's been collected by digital devices, whether they're computers or the internet or your cell phones. And that massive data is now collected and stored somewhere in the cloud. And so this massive data is available. In order to make use of this data, which is stored in the classical domain, we actually have to analyze the data. And this data analytics, means you have to crunch these numbers and think about what is a pattern that you find in this massive set of data. And then once that pattern, the goal of the analytics is to come up with a model. And this is a model that captures very effectively the structure of that data inside that is stored in the nature of this massive data. And once you actually have a model, then you can actually start to make predictions, okay, based on this. So for example, if I go to internet shopping malls and do various types of shopping, then I generate a lot of data, and the AI company can actually start analyzing my pattern of consumption or shopping, and then it creates some kind of a model of the tendency of what I like to buy and what I don't like to buy, and based on that, it can actually make predictions of the next set of things I will be interested in buying, or new products that I will be very interested in learning more about. And once these predictions are made, then you can actually use that as either a marketing tool or suggestions or make recommendations. And this type of analytics is done all the time. Now, today in machine learning, we actually use some of although these models are getting more and more sophisticated, the types of models we can build is actually relatively simple. And if you actually go to quantum domain and try to build quantum mechanical models, you can actually potentially build much more precise and sophisticated models to make better predictions about the big data. So this is an example of how quantum computers can potentially be utilized in artificial intelligence and machine learning. So these types of quantum computers can actually start to address applications that we thought was not very feasible in the past. We, first of all, some of our technology uniquely has this reconfigurable nature, in the sense that we don't actually have to build a customized chip where all the information is printed, or the capabilities are printed onto the chip. All of our computation can actually be programmed by programming these laser beams entirely in the software. Some of the possible industries that we can potentially address includes pharmaceutical industry that are interested in this molecular design to make specific reactions with the molecules that are inside our body. And then drug delivery and drug discovery tends to be a very computationally intense problems that we don't have very good solutions to. Energy sector, in the energy sector, we are interested in making more efficient solar cells, for example, to capture the energy, the solar energy into electricity. Or we're interested in carbon sequestration, where we try to capture carbon from the air, from the global, the greenhouse gases, and try to embed it back into the ground. Or we want to try to think about better chemical reactions to maybe create better fertilizers. All of these are massive computational problems that have a huge impact in our everyday lives. We are doing some of these things extremely inefficiently because we don't understand the underlying physical principles and chemical reactions of the materials. So material design and chemical processes is another large area of applications. In the transportation industry, there are a lot of logistics problems. As these automobiles navigate, or if you actually have multiple places you have to deliver packages, all of those optimization turns out to be a very difficult problem, where optimal solution is hard to find as the problem size gets bigger and bigger. So there are massive opportunities for new computers to come in and provide efficient solutions. And then finally, in the financial industry, the optimization of portfolio management turns out to be a difficult problem. Making some predictions about the markets, how different derivatives will move into the future. Now, those are very complex problems with lots and lots of different possibilities. And those optimization problems can also be potentially tackled by quantum computers. So the key message is quantum revolution is here. If you think about the 18th and the 19th century as the industrial age, where energy that's extracted from fossil fuels actually were utilized to build machines and transportation systems that worked, that actually led to a huge economic growth for mankind. And then last maybe 50 years was truly information age, fueled by the semiconductor transistors and Moore's law. It has brought about tremendous amounts of both computational and communication powers that currently fuels our economy. But I think the quantum age is here. We're at the very beginning of a quantum age. If we can actually make some of these quantum mechanically capable computers to work and to scale, it will actually unlock tremendous amounts of opportunities in energy, medicine, material science, machine learning, and artificial intelligence that we do not think about being feasible today. So I think there is a tremendous amount of opportunity to embark on this new era, and we're very excited to be taking these opportunities. So as I wrap up the story about our technology and where IonQ is headed, I would also like to share just a few minutes my personal experience of how do we take on these very massive challenges. Now, quantum computing is one of those things where about 20 years ago, when I was a young graduate student studying physics, it was just a scientific fantasy. People did not know something like that could be built. There were ideas that this could be useful, but nobody had any compass of exactly what to do to get this to work. So in some sense, it was a massive challenge, and therefore the success of the opportunity was not very visible. But at the same time, it was a massively large opportunity. If we can actually make this to work, we can actually have a huge impact on how the world economy runs. So sometimes we have to think about these very big challenges where not just me, but nobody else knows how to tackle these problems. And then I think in order to be extremely effective in trying to create these opportunities to come to fruition, I think you have to train yourself with, in my mind, two things. One is we have to understand the fundamentals of science or knowledge. We have to always stick to the facts and the knowledge that it provides. And then you also have to be extremely creative. In so many cases, I see some of the brightest scientists who are so well trenched into the knowledge that's known today, but not having an open enough mind to things that can be made possible. That they sometimes don't look at the opportunities or have the courage to jump. So I think it's very important to always keep an open mind, and take on the challenges as something that we can influence into the future. And then once you have some confidence that you can tackle the problem, I think sometimes it's very important to start jumping in with both your feet, take some risk, and try to see if you can make some progress in that area. Because the minute you take on challenges that nobody else has taken on, that I think is where the real opportunity is. And sometimes the future is uncertain, but uncertain future is the only thing that's sure, that's certain about future, is the fact that it's uncertain. So sometimes you don't take on the premise that future is there for you, it's already determined and made for you. You can sometimes go and influence the future. So take on those challenges, have an open mind, dive into the future, and try to see if you can create solutions. So I would like to thank you for all of your attention. Here is my contact information, kim@inq.co. Feel free to send me questions or any suggestions. I'd be happy to answer any questions for you.